Good morning, AP Physics students. Okay, so today we're going to continue with our Unit 2 notes on linear motion. And we've already looked at the definition of constant velocity. All right, I'm going to put them right up here. Oh, well, here it is. Constant velocity, that was V equals displacement divided by time, because it's a rate. And we've already seen the definition of uniform acceleration. That's A equals V sub F minus V sub O over T. Both vector formulas. Now, there are two other equations that we use in linear kinematics, and there's a reason for that. For example, what if you're accelerating and you want to know how far you've gone? Well, there's no D here, and we can't use this to get it because this is for constant velocity. So what do we do in a situation like that? Well, simple. They did some finagling, and I could go through a math proof to show you how they came up with it, but we don't need to worry about that. We just need to understand how to use it. The first formula we're going to look at is called the general equation for linear motion. Well, I call it that, but it looks like this. The displacement traveled is equal to the initial velocity times the time period. Oh, look, there's your constant velocity part. But now this V sub O is not going to stay the same. It's going to change because you're going to be accelerating. And that's what this part is for, 1/2 AT squared. So this actually solves all possible cases for motion in a straight line. You can find the displacement an object goes through if you know what initial velocity it has and what acceleration or deceleration it may go through. Okay? Now, these three work very well in helping us solve problems, but there is one little catch. If you'll notice, all three of these formulas are time dependent. You either have to know the time or the time is the unknown you're looking for, but time is in the formula. It's the only variable of all four variables, V, D, A, T. It's the only one that's in all three. So we've got a problem. There are sometimes cases where you don't have the time and there's no way to determine the time. What do you do then? Well, scientists realized that was also a problem. So what they did was they solved the definition of acceleration for t. They said t equals vf minus v sub o over a. And then they took that expression and substituted it in here. They squared, they did the FOIL method, they cleaned it up, and this is what was left. They got this. V sub f squared minus v sub o squared equals 2AD. We call this the alternate equation. It's your alternative when the time is unknown. It is time independent. You don't need to know the time in order to use it. Okay? Now, all four of these expressions work together to help you solve objects moving in a straight line. So let's look at some examples. All right. The first example I want to look at is a car that's moving 30 meters per second. So we are looking at horizontal motion. I'll speak for a few minutes about vertical motion in a little bit. We have a car moving initially at 30 meters per second, and it begins to decelerate at 0.5 meters per second squared. Now, if it's decelerating, that means the acceleration vector points the opposite direction of the velocity, and you're going to end up subtracting. So I'm going to let the forward motion be positive and the reverse motion be negative. Okay, so we'll let the forward motion be positive and the reverse motion be negative. Always when you start a problem, decide what directions, left and right, or if it's vertical motion, up and down are going to be. It doesn't matter what you choose as long as you stick with it. So I typically let the forward motion of the object be the positive direction, and of course the opposite direction would then be negative. All right, the car travels a distance of 50 meters during the deceleration. We want to know how fast will the car be moving at the end of the deceleration. We've read the problem. Our object of focus is the car. We can see it's decelerating from an initial velocity. And we need to go through a process here. So the first part is you look for numbers that you can identify. We have the car already is moving at 30 meters per second and it begins to slow down. So this would have to be V sub O, positive 30 meters per second. Here's another value. We can see that's the deceleration. So A equals negative 0.5 meters per second squared. We have one more numerical value, this, and that's the distance or displacement. We'll assume it's a straight line. So we get D equals, and it's still going forward, so that's going to be a positive displacement. All right, so it's like he looked up ahead, 50 meters ahead. He sees there's a light up ahead, so he begins to brake towards the light, and he travels forward 50 meters while slowing down. Okay? Now, I don't see any more numerical information. So is there any inferred information? Like, is the object falling? Is it coming to a stop? Well, actually, we don't know that it is. Not yet anyway. Does it start from rest? There's a number of different information that they can give you in non-numerical form, and I call it inferred information. Now, in this particular problem, I really don't see any inferred information. Usually, inferred information will take the form of the object is falling, the object starts from rest, the object comes to a stop. Those are what we look for to turn into numerical information, but there doesn't seem to be any here. So now we look, what are we trying to find? How fast will the car be moving at the end of the deceleration? That would be the final velocity. We need to determine what is that. All right, so now we look at this and we look at our four values here. Now remember, we're trying to find the final velocity. Notice the one thing we don't have, time. And we don't have enough information to get the time. We can't use the constant velocity formula because we're decelerating. And we can't use this one to get the time because we don't yet know VF. So we can't use any of these that have time, especially not this one. There's no VF in there to solve for, so we can't use that. That leaves this, our time-independent formula. So that's the one we're going to use. So I'm going to say VF squared minus V sub O squared equals 2AD. All right. We need to bring this to the other side to isolate our VF. So that's going to be 2AD plus V sub O squared. And now we can get rid of the square by saying VF equals the square root of the whole quantity 2AD plus V sub O squared. Now we can stick in our values. So we get 2 times negative 0.5 meters per second squared times, there it is, 50 meters plus 30 meters per second quantity squared. All right, and if we stick that into our calculators, you should end up, and double check it for me because sometimes I make a boo-boo, you should get 29.1 meters per second. Okay, so that would be, and notice it did turn out positive. We're still going forward. If it, of course, you're not going to get a negative value when you take a square root, so because that would give you an imaginary I. But we ended up with a positive value, so we are still going forward. We're just going slower than we were initially. All right. Let's look at another one. A train starts from rest and accelerates at a rate of 1.8 meters per second squared for a time of 8 seconds. Determine the distance the train travels during this time period. All right, again, first thing you do, you pick out the numerical information, identify it. 1.8 meters per second squared, that's acceleration. And the train is accelerating. So I'm going to take the forward motion of the train to be positive, and since it's acceleration, the increment you're adding must also be positive. All right? We have a time. It's going to accelerate for 8 seconds. Now that's all the numerical information I see, so there must be some inferred information, and yes there is. Look what it says. The train starts from rest. That tells us the initial velocity is 0, okay? When the initial velocity is 0, just write it down, go with it. Now, lastly, I think that's about all we can get from this sentence, so let's look at the last sentence. We want to find the distance or the displacement of the forward displacement of the train. All right, notice we have all 4 variables represented here. We have a D, a V, an A, and a T. I call those the DVAC variables. They're the big 4 variables that we use to describe any linear motion. We always have to have displacement, velocity, acceleration, time. Notice all 4, the only formula that we have that contains all 4 is the general equation. D, V sub O, A, and of course T. So that's the one we're going to use. That's the only one that has all 4. So we're going to say D equals V sub O T plus 1/2 A T squared. So that's going to give us, that drops out. 0 times T is 0. So we're left with 1/2 times 1.8 meters per second squared for the acceleration times T squared. And if you stick that in your calculators, of course, 1/2 of 1.8 would be 0.9, so 0.9 times 64, that would give you about 57 or 58 and 57.6 meters. Double check that for me. All right, there you go. Okay, so now we've used both of our new formulas in order to help us solve problems. The point is, when you're problem solving, you have 4 possible formulas to use. You must first identify what you know, what you're trying to find, and see which one it fits. It has to be one of the 4. So remember what they all describe: constant velocity, uniform acceleration. This one can be constant velocity. It can be starting from rest and accelerating, or it can be starting at some velocity and accelerating. But all 3 of these, you have to have the time, or it's the one you're looking for sometimes. If no time is involved, you have to use the time-independent formula, okay? Now, one more thing I'd like to discuss for a minute, and that would be objects that move in the vertical plane. Objects that are moving in the vertical plane. Let me get something to write on just to jot stuff down. Not that one. Let's use this one. Okay? Objects that are moving in the vertical plane. As long as there's nothing touching the object, we say that the object is in free fall. And you might want to jot this down somewhere. One of these days I'm going to remember to stick it in here somewhere. Free fall simply means the only force acting on the object is gravity. When that is the case, the object is said to be, the object is said to be in free fall. The only force acting on it is gravity. And gravity on Earth produces a specific acceleration. it produces what we call the acceleration due to gravity, and it always points towards the center of the earth because that's what masses do. They attract, they never repel. So if you have an object that is falling, it's said to be in free fall if the only force acting on the object is gravity. And for right now, you can assume air resistance is negligible because we haven't talked about that yet. So we're going to look at ideal circumstances, no air resistance. So the acceleration due to gravity actually uses its own special letter. It uses the letter G, which I think is kind of a problem actually, because when people see it, they want to call that gravity. That's not gravity. Gravity is a force. This is an acceleration produced by the force that's acting on the object. I hope you understand that. The value for the acceleration due to gravity at the surface of the earth is 9.8 meters per second squared, and that's the value that we will use. Now, if an object is in free fall, it can be doing one of two things. It can be going up with some velocity, or it can be coming down with some velocity. That velocity is going to be changing by increments of 9.8. Since I normally take the direction of motion to be positive, then in this case, we would have a negative acceleration because the acceleration due to gravity always points down. So here we would use negative 9.8 meters per second squared, and your velocity would get smaller and smaller until somewhere up there the object stops. And then it will begin to accelerate back towards the earth. When it accelerates back towards the earth, we could use down as positive, which means your acceleration due to gravity would also be positive if your letting down be negative. But remember, your choice of direction is arbitrary. Whatever you choose, you stick with it through that problem, and any vectors have to abide by the directions that you choose. So if you're choosing up as positive, then down has to be negative. If you're using down as positive, then the acceleration due to gravity would also be positive in this case. Okay, so this is how the velocity gets bigger as you fall. This is how the velocity gets smaller as you travel upward before you stop and begin to fall. Okay? All right. Oops, I didn't realize y'all couldn't see that. There it is. Okay, so what you guys are going to be doing tomorrow is practicing using our kinematics equations. You will have several sections with problems. You're not doing all of them, so make sure you pay attention to the instructions. But you will have one section where you will practice the definition of acceleration. You will have one section where you will practice the general equation and one for the alternate equation. Then you will also have a section where you don't know which one you're going to use. You're going to have to do what we did here. You're going to have to identify what you know and identify any inferred information, identify what you're trying to find, and see which formula it fits. Okay? That's what the last section will be. It will be, can you determine which one of those to use and then use it appropriately? Okay? Thanks for listening. Bye-bye.